All right, this will be the third video. We have 12 slides here. What is the correct Lewis structure for COCl2? Well, first thing, when you have these structures, chemical formulas, the element listed on the left is almost always going to be the central atom. So because of that, I would cross out 1. But because you have no indication of which is like central, the carbon or the oxygen. All right, that leaves 2, 3, 4, and 5. Actually, nope, 4 has an oxygen as a central, and so does 3. That leaves us with 2 and 5. When we look at COCl2, we have carbon in group 4, oxygen is in group 6, and chlorine is in group 7. So this has 14 plus 6 plus 4 is 24 electrons. When we add them up, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 for molecule 2. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 for that. Well, so they both have the right number of electrons. So the next thing is structurally, which one is correct? Well, if we look at molecule 5, the carbon there has only 6 electrons, whereas in 2, it has 8. The chlorines have 3 lone pairs and a bond. The oxygen has 2 lone pairs and 2 bonds, so there's your correct structure. Technically, in this case, that oxygen would be negative and the carbon would be positive, and 2 and 5 are actually resonance structures of each other, but you'd want to pick compound 2. Next, which of the following compounds has 2 lone pairs on the central atom? When you draw CO2 out, you would get this structure. So it's not that. It's SCl2. By the way, it has 2 lone pairs. Make sure you're clear on that. Anytime you're drawing a halogen, expect 1 bond and 3 lone pairs on those vast majority of the time. We have sulfur in group 6. There's 2 chlorines, so this has 20 electrons. If you look at what we've got here, there's 2, 4, 6, 8, 10, 12, 14, and 16. So we are 4 electrons short, which makes this have 2 lone pairs. So that's one of them, and that is actually the only one. If we do NF3, again, the halogen here, fluorine, they're going to have a single bond and 3 lone pairs. The nitrogen, 3 bonds, 1 lone pair. So no. Carbon disulfide. Well, sulfur and oxygen are in the same group of the periodic table, so that one would look, like CO2. There we go. And I keep wanting to put oxygens in there, but that would be carbon disulfide. And then in SO3, you've got 6 from the sulfur and 18 from the oxygens, again, for a total of 24 electrons. Turns out you'll have double bonds to each of the oxygens like that. The sulfur will have actually a 0 formal charge in that state because sulfur is in group 6 and it has 6 bonds. Sulfur can have 6 bonds because it's in the 3rd row of the periodic table. So here's its valence shell configuration, but keep in mind it has empty d orbitals. So we haven't really talked about it, but it would hybridize the S, the 3 Ps, and 2 Ds in order to make this structure. And we're not going to worry about that. But there's your structure for it. It has no lone pairs on the sulfur, so there you go. If you left off the double bonds, it would still be trigonal planar around the sulfur, and it would have the correct number of electrons, but the sulfur would end up having a 3+ charge there, which is bad. Let me see. Actually, I need to count the electrons, so let's do that. We have 2, 4, 6, 8. Times 3 is 24. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And so the sulfur, again, like I said, would have a 3 plus, which is just bad. That's why this one is going to be preferred. So again, just SCl2. What is the formal charge of the nitrogen? Well, the formal charge of the nitrogen will be that it's in group 5 minus it has 4 bonds. There are no lone pairs shown because it has an octet. It's not implied either. So there are no non-bonding electrons, so it's +1 or 1 plus. Which of the following structures have 0 formal charge on carbon? Remember, carbon is in group 4, all right? And we're assuming that everything is shown here. All lone pairs, all radical electrons, all hydrogens. So molecule 1 would actually have a positive charge on the carbon because it only has 3 bonds. Molecule 2 would have a negative charge because it has 3 bonds and a lone pair. 4 minus the 5, 3 lines and 2 dots, would be -1. So it's not anything with 1 or 2 you could eliminate, and therefore we know it's 3 and 4. But just to prove that, you have 1, 2, 3, and 4. So that one is neutral. That's a radical carbon bonded to 3 hydrogens. And then you got 1, 2, 3, and 4. That one we call a carbene. So it has 2 bonds and 1 lone pair. It only has 6 electrons. This only has 7 electrons. This only has 6 electrons, but technically those carbons are neutral. Which of the following structures have a 1 plus formal charge on a sulfur atom? Sulfur is in group 6, so you want to have either 6 bonds or 4 bonds and a lone pair, maybe 2 bonds and 2 lone pairs on sulfur. So if you look at this structure, there's 2, 4, 6, and 7, so that'll be -1. 1, 2, 3, 4, 5, 6. So we have 2 there as a good answer. 1, 2, 3, 4, 5. So no. 1, 2, 3, 4, 5, 6. So that's correct. And then 1, 2, 3, and 4. So the answers are just molecules 2 and 4. What are the formal charges on boron and oxygen in the following structure? Well, we've seen a lot of these, but excuse me, oxygen with 3 bonds and a lone pair, you have 6 minus 1, 2, 3, 4, 5. That's going to be +1. So based on that, you can eliminate those. And now the boron is either 1 minus or 1 plus. Well, boron's in group 3. So 3 minus 1, 2, 3, and 4. 3 minus 4 is -1. So here's your correct answer. What is the correct Lewis structure for nitric acid, including formal charges? Well, we have hydrogens in group 1, nitrogens in group 5, oxygen is in group 6, and there's 3 of those. So 18 plus 6 is 24 electrons. If you count them up, and in these molecules, you got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So no. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so just by counting, we could eliminate at least one of the options there. Let me erase the mess. All right. Molecules 1, 3, and 4 each have hydrogen. They each have 3 oxygens, but molecule 3 has an oxygen in the middle, and you may know that nitrate is a polyatomic ion. Nitrogen's on the left. It's going to be the central atom. So there you go. That's gone. And now we have one more issue to look at. Molecule 1 has a nitrogen with 5 bonds. 1, 2, 3, 4, 5. And so that violates the octet rule. And so 4 is correct. Without going through the procedures to figure out what its structure should look like, you could analyze the ones given and figure out why they're wrong using the logic I used there. All right, bottom question, what is the correct Lewis structure for SCN minus, including the formal charges, if any? So this one, it's called the thiocyanate ion. Sulfur is not the central atom. So this is actually one of those exceptions where the one on the left is not central. It's in the order there, and you have SCN for each of the 5 molecules given. So we got sulfur in group 6, we've got carbon in group 4, we've got nitrogen in group 5, and then we have a negative charge. So this has 16 electrons. Let's count up 2, 4, 6, 8, 10, 12, 14, and 16. 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14. So hey, we could at least eliminate 2 options just by counting carbons. So 2 and 5 were not it. All right, next, let's look for octets. All right, so we have 3 lone pairs and 1 bond. Carbon has a single and a triple. Nitrogen, this is in molecule 1. Nitrogen has 3 bonds and a lone pair, so those all have octets. In 3, we have a carbon with a triple and a double bond, so that has 10 electrons and violates the octet rule. In molecule 4, we have a carbon with just 3 bonds. It only has 6 electrons, so the answer is 1. Which of the following is the correct representation of dipole for the phosphorus-chlorine bond? All right, so phosphorus has an electronegativity of 2.19 and chlorine has an electronegativity of 3.16. So the difference in electronegativities is 3.16 minus 2.19, which is going to be, let's see, 0.97, there we go. And chlorine's more electronegative, so it's going to go in the direction of the chlorine, which makes the chlorine partially negative, the phosphorus partially positive. In that case, you see I'm just right above there, molecule 5 doesn't have the positive or minus. In 4, they're both minus. In 1, they're both positive. And then between 2 and 3, you just match up its compound 3, or bond 3. All right, which atom has the most partial positive in the following compound? Well, we have bromine there with an electronegativity of 2.96. Carbon is 2.55. Nitrogen is 3.04. And oxygen 3.44. Well, so carbon is giving up electrons to the nitrogen. Nitrogen's giving up electrons to the oxygen. So the nitrogen is kind of giving, but it's also taking. So it's not the nitrogen. The oxygen is the most electronegative one in here, so it's not the oxygen either. So we could cancel those out. But we do have a carbon giving up electrons to the boron above and below it, and to the nitrogen to its right. I shouldn't have deleted that. There we go. So the answer is carbon. Yeah, there's a hydrogen giving up some electron density to the carbon, but it does have 3 more electronegative elements pulling from it. And even the oxygen, through induction, is pulling electrons even further away from the carbon from a distance. For the following compound, identify the polar covalent bonds and indicate the direction of the dipole moment using partial positives and partial negatives. Well, again, we have chlorine with an electronegativity of 3.16. We have carbon with 2.55. Hydrogens 2.20. And oxygen 3.44. You see that if we look at this carbon there, it's surrounded by 2 carbons and an oxygen. So just looking at that, the oxygen is the most electronegative, so it's pulling electrons above the carbon like that, which means you're going to get the partial negative here and partial positive down there. The right side of the molecule is just a methyl group, so that's not doing anything. And then the chlorine is more electronegative than the carbon it's bonded to, so it's going that way, making the chlorine partially negative, this carbon partially positive. If we were to do it for the whole molecule, well, we'd add those 2 arrows together. And so it'd be kind of in the middle and like this. That'd be the net dipole. But you'd have the partial negative end of the molecule and the partial positive end of the molecule like that. But by individual atoms, partial negative, partial positive, partial positive, partial negative. For NaSCH3, draw Lewis structure and identify each bond as polar covalent, non-polar covalent, or ionic. Well, we have a sodium there, so there's going to be ionic somewhere. And then we have SCH3. Because that sodium is sodium, it's going to have a 1+ charge, meaning the SCH3 is going to have a negative charge. So we've got sulfur in group 6 plus carbon in group 4 plus 3 hydrogens plus 1 electron is going to give us 14 electrons in the SCH3 minus. So we have S, let me do it like as a Lewis structure, SCH3, and then give the sulfur 3 lone pairs. Count up the electrons, we get 2, 4, 6, 8, 10, 12, and 14. So that does match our count of electrons. The sulfur would have a formal charge of -1 because it's in group 6. And so it would be 6 minus 2, 4, 6, and 7. 6 minus 7 is -1. All right, now going to electronegativities. The sulfur has an electronegativity of 2.58. Carbon is 2.55, 2.20. So what I'm going to do here is highlight these bonds. Well, really all of those are going to be non-polar covalent. And then the sodium and the sulfur would be ionic. There are no polar covalent bonds. What is the hybridization state of carbon 1 in the atom or in the following compound? Well, it's got electrons coming off in 1, 2, and 3 directions. And when that's the case, always sp2. It has 1 sigma bond here and 1 pi bond. Anytime you have a single pi bond, it must be sp2 hybridized. What is the hybridization of the nitrogen in this compound? Well, again, it's got electrons coming off in 1, 2, and 3 directions. So it's sp2 hybridized. It has, to the left of it, 1 pi bond, and there's no others, so it's just sp2 hybridized. Which of the following structures have carbon with sp2 hybridization state? Again, when you have that, you're looking for electrons coming off in 3 directions. And the first one has that. Here we have 1, 2, 3, and 4, so no. 1, 2, 3, 4, so no. 1, 2, and 3, so yes. the carbon 2 bond in the following compound results from the overlap of which orbitals? So they're talking about that bond here, and it says which orbitals. The options are sp to sp2, sp to sp3, sp2, 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 sp3, sp3, sp2. Well, let's think about like at least eliminating stupid choices. You know, if you have sp hybridization, the molecule is either going to have a triple bond or a double bond next to another double bond, like this. The middle one would be sp hybridized. And this doesn't have that. And even if we were trying to consider resonance issues like this, it's not a possibility in this case. So the first two there are just bad. The next is like, are there sp3 orbitals? They each have sp2 as an option. But is there sp3? And the answer is yes. Because we have carbon 1 with electrons coming off in 1, 2, 3, and 4 directions. And then carbon 2 has electrons coming off in 1, 2, and 3 directions. So that'll be sp2. And carbon 1 is sp3. I'm assuming, they're going in that order. Like this is carbon 1 on the left, while those on the right are carbon 2. So based on what we did first, we saw carbon 1 was sp3 hybridized. That was enough to finish it. How many pi bonds are present in this compound? Well, we have a pi bond here, pi bond here, pi bond here. There's going to be a pi bond there, and there's going to be 2 pi bonds here. So we have 3 in the ring and then 3 others, so there are 6 pi bonds. Which of the following best describes the orbitals involved in the formation of CO double bond in acetone? Well, you have carbon. I would never ask this question on your test, but it's 1s2, 2s2, 2p2. And the oxygen is 1s2, 2s2, 2p4. All right. When we look at the orbital diagrams, let's do carbon in the valence shell. And then oxygen. They're bonding the p part, but they're also hybridizing. All right, the carbon is sp2 hybridized. The oxygen's also sp2 hybridized. So we're taking those, we're taking these, and hybridizing them, whatever. We could go into craziness here. And we have a carbon with a p orbital here. We've got an oxygen with a p orbital there. Those are going to overlap above and below to create a pi bond. You also have an sp2 orbital for each of those, combining in the middle to make a sigma bond. Now, so which of the following best describes the orbitals involved with the formation of the CO double bond in acetone shown below? Well, if we look at this, it's like sp. We have technically 2 sp2, and same with the other one because they're both from the second energy level. Okay, I see. So they have the sigma bond is between sp2 and sp2, and we see that here, there, and so these are wrong. And then the pi bond is pi bonds are always p, so this is correct, and this is wrong, and so that is the top one is not the right answer. It's just the one there. I wouldn't ask you a question that looks like that. I might just ask for the hybridization. I rank the indicated carbon-carbon bonds in increasing order of bond length. So what I'm going to remind you here is that an sp3 orbital is going to be bigger than an sp2 orbital, which will be bigger than an sp hybrid orbital. And the reason is the amount of s character. With sp3, you're combining 3 p's and an s, so it's mostly p. All right, so you get this bigger lobe. With sp2, you get 2 p's plus an s, so it's still mostly p, but then with the sp, you get one of each, a p and an s, and therefore it's just smaller. And I'll remind you that the p's are bigger than the s's. So if we're combining all those together, the p's stick out further away from the nucleus than the s orbital does, and therefore the more p character there is, the bigger the orbital. And the bigger the orbital, the longer the bond is going to form. So now, when we look, we have an sp2 hybridized carbon here, an sp hybridized carbon there. We have sp, sp3, and sp3. So carbon 3 is the longest, but the question says in order of increasing. So we want to go for the shortest. We're looking at this bond, and that bond. So the triple bond would be the shortest, but it didn't ask for that bond, just FYI. So we have bond 1 is sp2 and sp. All right, that's 1. Bond 2 is sp and sp3. Because it has sp3, 2 is going to be longer than 1. And then bond 3 is between 2 sp3s. So the shortest is the black one, bond 1. That's shorter than 2, which is shorter than 3. Which of the following compounds have trigonal planar molecular geometry? I could look at this in 2 ways and just say the base geometry, or I could look at it in terms of the actual, what we would actually name it. You know, the base geometry includes lone pairs, but the actual structure's names will be excluding the lone pairs, which, again, I don't love that, but that's the way that chemists do it. So we have a carbon here with 1, 2, 3, and 4 different directions electrons come off, so that's tetrahedral. If it was drawn, you would draw the tetrahedron like this, and it would be trigonal pyramidal, so it's not 1. The oxygen here would be the same thing. The boron has electrons coming off in just 1, 2, 3 directions, so it's trigonal planar. You know, if I'm being extra specific, the carbon here's sp3 hybridized, the oxygen's sp3 hybridized, the boron is sp2 hybridized. The oxygen in 4 has electrons coming off in 1, 2, 3, and 4 directions. And so it's in a tetrahedral geometry, but in reality, it's going to be bent triatomic. And then 5 has electrons going in 1, 2, and 3. And so that one is also trigonal planar. The carbon here is sp2. The oxygen here is sp3. All right, following is the structure for propranolol, an antihypertensive drug. What are the hybridization state, molecular geometry, and approximate bond angle at the indicated nitrogen and oxygen atom in propranolol? Propranolol. Propranolol. There we go. All right, so First of all, we need the hybridization state. If you look at the oxygen, there's electrons in 1, 2, 3, and 4 directions. That means it's sp3 hybridized. The nitrogen has 1, 2, 3, and 4 directions of electrons, so it too is sp3 hybridized. We need the molecular geometry and bond angle. Well, because it's asking for them, but they're both sp3 hybridized, I'm going to say the base is tetrahedral for each. That's like, and I'm doing that because that helps you figure out the bond angles. They're sp3 hybridized, so they're tetrahedral, but the molecular geometry is going to be bent triatomic for the OH there, because it only has 3 atoms, 1, 2, and 3, and they're bent. We exclude the lone pairs. And then the nitrogen has 1, 2, and 3. Now, for this, if I look at the oxygen, you have the hydrogen, the R group. The lone pairs would be in the wedge and the dash. So there's your tetrahedron and the bent triatomic at the same time. Now for the nitrogen, its molecular will be trigonal pyramidal. And I could draw the hydrogen. I'm going to put the R group over here, and then CH3, which is this CH3, and this will be representing the R, and then you've got your lone pair up there. So it's trigonal pyramidal. The R group, the hydrogen, and the methyl group are each below the nitrogen. The hydrogen is to the left of it and in front of it. The R group is to the left of it and behind it, while the methyl group is to the right of it, but in the plane of the nitrogen and the lone pair. So up here, I would say what they're going for is like not the base geometry, but overall. And that actually didn't make any difference in that one anyways, but the bottom it did. All right. Which of the following compounds has a net dipole moment of 0? That means the dipole moments are going to cancel out. Fluorine has an electronegativity of 3.98, carbon 2.55. The lone pair here is going to go in that direction. The dipole moment is going to go in that direction. So those cancel out. So 1 has no dipole moment. In molecule 2, you have up and to the right, down and to the right. So the net dipole is going to go in that direction. Let me show you something over here. If I take this and I move it over there, they're equal in magnitude but opposite in direction. So the tug of war of electrons has canceled those out. 2 has a net dipole moment to the right. 3, you have down and to the left and down and to the right. And I'm going to try to be consistent with my colors. The individual bonds will be in red. The net dipole moment will be in blue. And so it'll just be down. The left and right parts for those bonds cancel out. And then for 4, you have up and to the right, down and to the right, and then down and to the left. These two cancel out, leaving you with the other one. And so the net dipole moment is in this direction. Now, for the last one, you have chlorine that has an electronegativity of 3.16. And I'm not going to worry about the carbons, but 3.98 for fluorine. So let me show you this. I could do the thickness and the length representing the dipole moment for the fluorine versus the same thing for the chlorine. It'll be shorter and thinner. So it'll, like, this is up and to the right and that's down and to the left. They'll cancel out a little bit, and I didn't do the right colors, so let me fix that. There you go. Which means the net dipole moment will be somewhat in the middle in magnitude between them, but down and to the left. And finally, rank the following compounds in order of decreasing highest to lowest dipole moment. So what we have here are really just the two CO double bond groups and their effect on polarity. Oxygen is more electronegative than carbon, so you're getting in that direction versus this. So the net dipole will be in the middle like that. For here, you have up and down. So those are going to have a 0 dipole moment. And then in this molecule, you have just up. And I've got out of the color thing, but the net dipole moment here, because the middle one didn't have a net, so I'm not going to go back and fix that. But you have there, you've got here, and then the net dipole moment will just be in the middle of them. Now, how do you compare 1 and 3 together? Well, in 1, this has a Y component, and that's in the positive direction. The other one goes to the right and a little bit down, so there's a negative Y. But it's not fully canceling out like this in 2 is, right? Because it's not up and down. In 3, you have a positive Y and also a positive Y. So those are actually adding together, which means that 3 has the highest, and we're going from highest to lowest, so 3 is greater than 1, which is greater than 2, which has no dipole moment. All right, that is it for this video. See you in the next.